Alrighty then. Let's take a gander at description of functions, and specifically 3 ways to describe or 3 ways we can represent functions. Numero uno, we can make a table. We saw those earlier already. You have an X and you have an input, you have an output. We can also write them as a rule, or more specifically, some people call that thing the actual function. But it's kind of like an equation, you know, a function equation. So oftentimes people will say the function when they say f of x is equal to 2x or something like that, right? So they call that the function, even though we're representing the function as a rule or an equation. And lastly, we can do graphs. So 3 different ways to represent the function. So let's look at example number 3 here. A rule for the function graphed at the right, actually under and right, is y equals 2 to the x minus 4. We're going to find the domain and the range of the function. So you don't need to understand right now where this graph comes from this function. We're just saying that when you graph this, you get exactly this shape here, this graph. So we just want to know what the domain is and what the range is. And this is how I like to visually think about domain and range, okay? Let's pretend you have a flashlight, bloop, 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 bloop. And you shine the flashlight underneath or above the function, right? So it shines a light. What's going to happen is that you're going to get a shadow. You're going to get a shadow on the wall right there. And same thing, when I take this and I shine my light from above, like so, eventually I'm going to get a shadow that shines down, like that. Because this guy here goes forever out, and it goes forever up. It goes slowly out. It goes slowly out. Sometimes it's going to take a long time to get out to here because it's going up much faster. But the domain would be what are the numbers here that get shaded if you project a kind of a shadow on the wall, and the wall being the x-axis. Well, the domain here would be all real numbers. And the way that we can write that is just an R with a second leg. All real numbers. Why? Because when I zoom in there, it includes all these numbers here. 0, 1, but it also includes half. It includes 0.002, etc. So it's every single number on that number line there. And the way that I visualize domain is the exact same thing, but this time what I do is I just move the flashlight somewhere else. And now I move it this way, and I'm going to shine it and see what happens. When you shine it like this, then this wall gets a shadow. And again, if you do it on the other side as well, this wall gets a shadow with no breaks. So that means the entire, because, I'm wrong. Notice here that this actually doesn't ever get below over here. It's hard to tell, but it doesn't go below. So let me clean that up here. Doesn't actually go below that. So the lowest it goes is this point right here. All right, and I do want to clarify here that when I am shining the light from the other side, notice what happens is that the shadow still comes down a little bit more to here, right? Something you don't know offhand, or we can see it on a graph if I open up another one, but notice this here. This can never, ever, ever, ever equal 0. No matter how big or small of a number, no matter how negative I make the x, this can never be 0. So in other words, this can never also get into the negatives. So in other words, it'll never be 0 minus 4. I'll show you on a graph in just a moment. Actually, let's open that up now. That's Mazdagam. Okay, and graphing calculator, and let's do 2 to the x, and then minus 4. Now, no matter how much I zoom out, look, and zoom this way, and I'm moving it, you just can't see, it never goes beneath that line. And in fact, it never even touches that line. Which line does it never touch? It never touches this line right here, all the way across. So that means the domain is all real numbers. I can put any number I want in, but only certain numbers come out. The range is going to be all real numbers, except it has to be, y has to be greater than negative 4. Because y will never get to negative 4 or negative 5 or negative 6, any of those. Now again, that might be hard to have known because of the nature of the functions. Maybe you don't know that this graph approaches the line, but it never touches the line. That has a special word. It's called asymptote. Let me spell it, but you don't have to write it right now. Asymptote. It approaches it, but never gets there. It approaches, but never gets there. We're going to deal with that later on in this class. But there we go. All right. So with example number 4 here, find the domain and range of the function with this rule here. So you ask yourself, what kind of numbers am I allowed to put in? Are there any restrictions? And what kinds of numbers do I get out? So you can either just logically think about it, or you can actually pull out a graphing calculator and check to see what the graph looks like. So go ahead and take a moment and consider that. So what I did was graph the function, and I just used Desmos, but you're welcome to use your TIs. And notice, and again, this is hard to tell unless you zoom in and zoom out, is that this does go forever up. It goes forever up, but it has a floor. The lowest it gets is right here. That's my minimum. The lowest it gets. So in terms of my flashlight and my domain, any number can go in. Any number can go in. Because look, if I were to project the shadow down below, this continues to open out. So that means there'll always be a shadow down there. So my domain is essentially all the real numbers. Domain is all real numbers. But the range is all the real numbers such that y is greater than or equal to the negative 1. It actually touches the negative 1. If you recall, this is called my vertex right here. And it does touch that negative 1. The graph up there is a little bit off on my board. It's not off. So, and so there we go. It's all real numbers greater than or equal to negative 1. If you don't want to plug it into a calculator, that's okay. You can think about it logically. Notice there's no restriction on this x. What do I mean by that, a restriction? Well, if I had said this, 2 divided by x, a restriction right there would be x could never be 0. Because if it were, you get that beep, 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 right? Same thing here. If I had a function that was the square root of x, something I wasn't allowed to put in, x can't be negative. Because the moment you have a negative number, you're now outside of the real numbers. You're in imaginary territory. So domain, you can just think logically. And I'll give you a hint here. Probably 99% of the time, domain is going to be all real numbers. Most of the time, it's going to be all real numbers. Especially when you're given a rule like this. Okay? On a graph, your domain might not be, depending on the shape of the graph. But with a rule, almost 99% of the time, it's going to be all real numbers. All right. If you recall, vertical line test, as I said at the beginning of the lesson, which of these is a function and which is not? Well, so if we look here, 15 is a function because no matter how many vertical lines I pass through this, every single time it intersects at most once. Oh, but Swenson, it doesn't intersect anything over there. You're right. So there's no data. All right. And as we look at number 13, it's not a function. Here, it behaves like a function because it doesn't intersect at all. Here, it behaves as a function. Why? Because it intersects exactly once. But here, it doesn't behave because it intersects more than once. All right, so which are functions? 15 is a function, and that's it. So 13 is not a function. As we can see, 14 is not, and 16 is also not. I do want to point out to you, it might behave as a function in certain places, right? So look at this right here. This behaves as a function here, behaves as a function here, behaves as a function here. In fact, an infinitely number of places it behaves as a function. But inside here, clearly it intersects 3 times, so it's not a function. But everywhere else, it feels like a function. Over here, over here, over here. Outside that middle part, it behaves like a function, but in one place it doesn't. All right, the last thing that we want to talk about is how do we name and evaluate functions? So, functions can be named with letters such as F or G. Those are the most common, F and G and H. So just like we'll say X is a variable, F tends to be F, as in Frank, tends to be the symbol for a function. And so we say this. How we read it is F of X. So this here, we read F of X. F of X. Another thing you can call it is a domain whose name is function and the independent variable is X, right? That's a more complicated way, but simply F of X. And X being the independent variable, F being the name of the function. So, suppose F is defined by the rule F of X is equal to 4 times 1/2 to the X power for all real numbers X. Let's evaluate F of 5. So all this simply means is you take this value and you substitute it into wherever you see an X in the function. So it's going to look like this. And this is how we can show our work too. So make sure that we show our work in a similar fashion. So I'll say F of 5 is equal to 4 times 1/2 to the 5th power. You can plug all that into your calculator right now. Boom, just plug it into your calculator to get an answer of some kind. When we plug this all into a calculator, there are a couple ways you can answer this question as a decimal, 0.125, or you could say the answer is 1/8. Either one is sufficient. In other words, when I like this function notation because it shows you when I put in a 5, out comes a 1/8. Or when I put in a 5, out comes a 0.25. So I would write the answer and just box or circle this as my answer. Again, feel free to plug that all into your calculator. So this is showing your work from here and then jumping using your calculator from there. All right, now let's evaluate the nature of functions. The nature of functions. Is it true that when I plug in 2 values added together on the inside, that's the same as adding 2 functions together? Is it true that when I do that? So we're just going to test it real quick. So that means this one is going to be F of positive 1. And the question is, does it equal F of negative 2 plus the F of 3? So I'm going to do all 3 of these and see what happens when I put that into my calculator. So let me substitute in 4 times 1/2 to the 1st power. Does that equal 4 to the 1/2 times negative 2, or to the negative 2, plus 4 to the 1/2, times 1/2 to the positive 3? I can evaluate this by hand right here. This one here just becomes 4 divided by 2, which is just a 2. And does this equal here? This one here, negative 1 to the 1/2 to the negative 2 means take the reciprocal and then square it. So it's actually 4 times 4, so this is a 16. The 3 here makes this 1/8, 1 over 8. And then 4 times 1 over 8 is 1/2. So clearly we see that 2 does not equal 16.5. What does this show? This essentially just shows that we can't just add the output together when we're thinking about adding the input together. It's not the same result. All right. And one of the last things we want to look at is a complicated situation where instead of substituting in a value for x, we're going to substitute another variable. So remember that f of x up there is going to be 4 times 1/2 to the power of x. And in this case, the x is n plus 1. So what do I write? I just simply write n plus 1 up there. And that's it. If there was something else to simplify here, I would simplify it. Now, theoretically, it's possible to simplify further, but all we need to do is just pause right there. Down here, when you substitute in, it's going to get a little bit more complicated. All right, so I want you to pause and take a gander at A and B first. And then together we'll do C down there. So go ahead and work through that. All right, so as you can see here, g of negative 2 is just positive 12. And next time I see you in class, we'll show you how to do this really quickly on your calculator. And then as we see, g of 1 is negative 3, g of negative 2 is 12, and g of 3 is 7. So in the end, that is not true. So let's see how to evaluate this larger function. It goes like this. 2 times 2n minus 1, quantity squared, minus 3 times 2n minus 1, minus 2. And how do we manage that? Well, you have to use your handy-dandy rules. If you recall how to multiply here a binomial squared there, I'm just going to do it and just trust me that this is the case. 4n squared minus 4n plus 1. Then I distribute the negative 3, so I get negative 6n plus 3, and bring down the negative 2. Distribute the 2 now, so I get 8n squared minus 8n plus 2 minus 6n. And I can actually combine like terms right there, so that's a plus 1. And now combine my like terms. This is like unto itself only, so I get 8n squared. These ones, negative 8n and negative 6n, are like, so that's negative 14n. And lastly, the 2 and the 1 are like, so that's a plus 3. So that is how we evaluate a function by substituting in more variables. My guess is this is going to be the most complicated thing you're going to see on the assignment and also on a quiz, which happens probably in a week or two. So make sure that you are checking your work when you see problems like this.